Hello and welcome to helpyourmath.com. In this video, we're going to look at verifying trigonometric identities. And this is part one of at least two because I found another one that's also called verifying trigonometric identities that I did. And you'll notice in that one that I had a huge sinus infection and I sounded terrible. So hopefully I sound a little better in this one than the other one. All right, let's talk about what we want to do when we're verifying trigonometric identities. Some strategies to consider when proving these identities: choose the complicated side to, quote, clean up. If both sides look messy, pick one, see what happens. Apply any of the fundamental identities. That's sine and cosine, cotangent and cosecant, tangent and secant. Convert all terms, factors to sines and or cosines. Look for opportunities to factor or combine fractions or multiply by conjugates or who knows. Try something. Dead ends can prove insights too. So if you hit a dead end, don't worry. Just see if you can learn from it and what you did wrong, and then go back and try it again. And also know that I will show one way to prove identities, but there are several ways to prove these identities. Generally speaking, when we're talking about proving identities, one side we don't touch at all. We only deal with one side. So we would just show that one side, and we would get it to match the other side. Okay, some of the trigonometric identities that we can use, we have our three Pythagorean identities, we have the reciprocal identities, and we have the quotient identities. We're also welcome to apply any mathematical strategies like the addition property of equality, getting a common denominator by multiplying by factors of 1, etc., etc. All right, let's jump into our first example. We want to verify this fundamental identity. And what we're going to do is we're going to not touch one side, and we're going to mess with the other side. So the side that already has the sine and only the sine trig function, I'm going to leave this one alone. So this one, I'm not touching. I'm leaving that one exactly as it's written. I'm going to do something to the left-hand side to make it look like that in the end. I think the first thing I'm going to do is the distributive property of division. So I'm going to take this denominator and I'm going to divide it into each of the two terms in the numerator. So that's going to give me cosecant of x over cosecant of x plus sine of x over cosecant of x. All right, cleaning up this, well, this is something divided by itself, so that's equal to 1, so that's great. What about over here? Well, if we jump back to that previous slide, look right here. If we have cosecant of theta or x or whatever in the denominator, that's equivalent to a sine of that thing. So having this cosecant in the denominator means that we would have another factor of sine in the numerator, and that would give me sine squared of x. And look at that. It's all done. It matches. Ta-da! Now, that was just one way, and again, there are many ways that we could have done that, but I found that to be the best for me. How about this example? Oh gosh, that left-hand side looks terrible. Let's see if we can make the left-hand side look like the right-hand side. So we're going to box this. We're not going to touch that. We're going to make this turn into cosine of beta over sine of beta. And one of the nice things about fundamental identities, proving them, is that you already have the answer. You know what you need it to look like. We just have to figure out what we need to apply to make that happen. Okay, so since the final thing that we're looking for is going to be in sines and cosines, I'm going to rewrite all of these so that they're all sines or cosines. So sine is fine, sine of beta. Cotangent, well, remember cotangent of beta is equivalent to cosine over sine. So cotangent squared would be cosine squared beta over sine squared beta. And then secant, that's 1 over cosine of beta. Okay, I'm going to put this one over 1 just so we have fractions, and then it looks like we have some simplifying. So I have 1 factor of sine up here, I have 2 down here, so that leaves me with 1 in the denominator. Here I have 2 factors of cosine beta. Here I have 1, so I can cancel out one of those. What am I left with? Cosine of beta over sine of beta, which is exactly what we were looking for. Voila. Last example. Why don't you pause the video and try this one? This was actually kind of a mean one to end on because it is a different strategy than the other two. What I notice here, so wait, first of all, I'm going to leave this side alone. I notice that both terms have a factor of cosecant, so I'm actually going to factor that out. Cosecant of theta, that would leave me with cosine squared theta minus, that would be 1 if I factor out the only thing that was over here. And then, okay, interesting. So I can rewrite cosecant theta as 1 over sine of theta, but what am I going to do about this cosine squared theta minus 1. It almost looks like a Pythagorean identity. So the Pythagorean identity is sine squared theta plus cosine squared theta is equal to 1. Now I want to use this to make it look like this. And I need cosine to be positive and the 1 to be negative. So I'm going to subtract sine squared theta from both sides. And I'm going to subtract 1 from both sides. That way, on this side, what do I have left? Cosine squared theta minus 1. Cosine squared theta minus 1. And over here, the 1's cancel, and I'm left with negative sine squared theta. Okay, great. So I can use the substitution property to substitute in negative sine squared theta, and I can put that over 1. Now I have a negative, but I have 2 factors of sine theta in the numerator and 1 in the denominator, so I can get rid of one of them, but that negative stays behind, leaving me with negative sine of theta, and it matches the other side. These have been a few examples of verifying trigonometric identities. Thank you for stopping by.